So now let's get at this idea of instantaneous rate of change. So average rate of change was between two coordinates because it was what was happening on average over an interval. With instantaneous rate of change, where we want to see what is our function doing at an instant, it's like we're going to be working with one coordinate. So what we're going to do is kind of start with just a graphical explanation here and what's coming through. What does our secant line do as we change to this instantaneous idea? So here we have just the graph x squared, so parabola opening upward through 0, 0. And first, we're just going to do a little bit more review of that average rate of change. So from x1 to x2, and that's the slope of the secant line between those two coordinates. So that's what we just practiced in that last video. So for example, the rate of change of f of x equals x squared from x equals 1, so that's that coordinate 1, 1, to x equals 2, which is 2, 4. If we took the slope between those 2 points, it would be equal to 3. And we could just check that by using that coordinate 1, 1, 2, 4, and calculating the average rate of change with the difference in y values, so 4 minus 1 over the difference in x values, 2 minus 1, so that's 3 over 1, which is positive 3. And then visually what we're getting, that secant line goes through those two coordinates there, and we can see that has a slope of positive 3. So that's our average rate of change, and what's happening is it's like, if we think in terms of time passing, it's like 1 second passed there. So moving from 1 to 2, it's like over 1 second. How did our output change? Well, it changed by 3. So now let's get this idea of what's happening at an instant. So the instantaneous rate of change of some function f of x, and now we're just looking at one coordinate, so at x1, is the slope of the tangent line at the point x1, y1. So notice we changed our terminology. Up above there, it was a secant line, and that's because it had two coordinates to go through. Now we're talking about a tangent line, which has one coordinate to go through. But what you might be thinking is, how do we draw a line with only one point? Typical rule of thumb is you need 2 points to graph a line. So this is where we need to, I don't know if creative is the right word, but we need to approach it in a very specific way. So what we're going to do is go back to this function x squared and focus at what's happening at x equals 1. So let me delete my secant line there, but I'll still have my coordinate at 1, 1. Now this idea of what's happening instantaneously is a very zoomed in idea. I'm going to take that very literally in meaning in terms of I have my whole parabola there, but I want to focus on what's happening at 1, 1. So I'm going to zoom in super close, and that's about all my computer will handle right here. If we were on Desmos, we could scroll and get super close. But what I want to do is think about a line that matches up with my function right here. If I imagine just right here something linear, even though there is this curvature to f of x, I want to think about what's a line that matches up at that instant at 1, 1. So what I could do, and it's a bit tricky on the screen here, but it's like if I had pencil and paper, what I would do is I would take a ruler or a straight edge, and what I would do is I would try to bump it up against the graph here to get it to line up as best I can. So going through that coordinate 1, 1, and then just matching the behavior of the graph. So what I'm going to do is I'm just going to kind of sketch here. And there's going to be flaws to this, but I'm going to get as best I can to kind of get an idea, and then I could zoom out and extend it further. Or maybe even I should use a straight line here. So maybe something like that. Okay, so I have as my parabola, and then at 1, 1, I have this line that's trying to match that rate of change right around that 1, 1 as closely as possible. So this is how I'm drawing a line with just one coordinate. It's I know I'm going through that coordinate 1, 1, but then in terms of slope, I'm trying to visually match up with the rate of change right around that corner, that coordinate. So let's go back to the explanation down here. So the instantaneous rate of change of f of x equals x squared at x equals 1 is 2. So let's talk about where this value of 2 is coming from. So again, my graph came out pretty good. So if I go up 2 and over 1, that should be a second coordinate for that tangent line. And as you can see, I was just a little below, and that's because there is some human error here. But roughly, that slope is a positive 2. So at this very moment, at 1, 1, the rate of change of the graph right there is a positive 2. So we're seeing how things are changing at an instant rather than over a period of time with a beginning and end. We can get this kind of, instantaneous view of how our graph is changing. So what we're going to do is in the next videos talk about how to actually calculate this, but it's this idea of being basically infinitely close to this point here and thinking about how is our function changing right at that point. It is going to still be the idea of slope. We're going to be thinking about how y is changing and how x is changing. So change in y over change in x. We just have to think about it a little differently with this idea of if we have two coordinates, how can we describe it in a way that it's infinitely close to each other? So a little snippet down here. We will spend a lot of time in business calculus determining functions that will give us slopes of tangent lines to get to a given function. The functions that give us the slopes of tangent lines to a function, which might all sound like gibberish, but we'll break it down quite a bit. But this idea of the slope of the tangent line, or this instantaneous rate of change, will also tie to derivative functions. So one last piece that I want to get at is here where we focused at x equals 1, so at that coordinate 1, 1, we had a positive value coming out, and it's because when we try to match up that slope, we have this positive instantaneous rate of change, which makes sense because the graph is increasing right there. Whereas if I looked at the tangent line at x equals, let's say, -2, so if I'm at -2, +4, and I try to graph the tangent line, so again, just trying to graph a line that goes through that point and then matches the behavior, that slope is going to be negative. And that's going to tie to the fact that over there, on that negative side, our function's decreasing. And then if we take a look at if we were at 0, 0, if we were at 0, 0, which is the vertex of our function, that tangent line is actually going to be perfectly horizontal. It's just going to go straight across. Because it's like if we zoomed in as close as we could to that vertex, it actually flattens right there. And as we talked about with graph behavior previously, is the fact that it's neither decreasing nor increasing right there. It's just kind of constant. And our constant function is a horizontal line. So these are the three types of slopes of tangent lines we'll see. We can have a negative slope, and that'll often be at a decreasing part of our graph. We could have a positive slope, which is coming from the increasing part of our graph. And then we could have a horizontal, which is coming from basically a turn in our graph where it's neither increasing nor decreasing. So just to finish up with this too, talking about these tangent lines. So with these tangent lines, it is just an equation of a line. We'd have a y equals mx plus b with these. The slope is what we were looking at here. That's that instantaneous rate of change that we're talking about. So if we wanted the slope, we'd have that instantaneous rate of change. We're also always going to have one coordinate to this tangent line. So we'll have some coordinate x, well, let's call it x1, y1. And that's going to be coming from the x value that we're given. So like -2, +4, or 0, 0, or 1, 1, coming from our f of x. And if we have the slope and we have a coordinate, then we could find b. So we can find this equation of the tangent line, evaluating that instantaneous rate of change, and then plugging in a coordinate to find out what our y-intercept would be.